Welcome to The Explainer. We're diving straight into the ultimate cosmic mystery today. I am so pumped to guide you through this because we're going to look at the math, the science, and the sheer wonder behind one of the most profound questions humanity has ever asked. We've got a seriously dynamic journey lined up to unpack the famous formula that literally frames our search for extraterrestrial intelligence. So, where are all the aliens? You know, what's really fascinating about this question, which you probably know as the Fermi paradox, is the mind-bending scale of the universe it forces us to confront. Physicist Enrico Fermi famously asked this over 70 years ago. If the universe is so insanely vast and old, shouldn't we have heard from someone by now? Is interstellar travel just impossible? Or are we literally all alone out here? I mean, think about it. With an estimated 100 billion to 1 trillion stars in our Milky Way galaxy alone, and with astronomers now confirming that most of those stars host exoplanets, the odds insist that we simply cannot be alone. There is just way too much real estate out there. But to bridge that gap between, hey, they must be out there, and actually finding them, scientists needed a framework. And that brings us back to 1960. A young astronomer named Frank Drake pointed an 85-foot radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani. This was Project Ozma, happening over at the Green Bank Observatory in West Virginia. He tuned into the 1,420 megahertz frequency, which is the natural emission frequency of hydrogen, thinking, any smart alien civilization might just use this universal frequency as a cosmic beacon. Well, he found nothing. But that nothing sparked a search that required a completely new way of thinking. Okay, Section 1, Anatomy of the Equation. Let's look at how we build this cosmic formula. So let's dive right in. The very next year, in 1961, Drake hosted a meeting of brilliant minds, including a young Carl Sagan, by the way, to figure out exactly how to mathematically organize this massive hunt. And out of that meeting came the legendary Drake equation. Drake essentially created a mathematical roadmap for astrobiology. The whole goal here is to estimate N, the number of transmitting societies currently broadcasting in our galaxy that we could potentially detect. Now, keep in mind, it was never meant to be a simple math problem you solve for a test. It was designed as a heuristic, a way to actually guide scientific discussions about extraterrestrial life. Frank Drake actually had a great analogy for this. He likened his equation to estimating a university's student population. Think about it. If you want to know how many undergrads there are, you just multiply the number of freshmen entering each year by the average number of years they stay at the school, right? Multiply the intake by the longevity, and boom, you get your total population. The Drake equation applies that exact same logic, just on a galactic scale. Let's see how this actually builds across three major scientific disciplines. First up, astronomy. You've got the rate of star formation, R star, the fraction of stars with planets, FP, and the habitable planets per system, NE. Then it funnels down into biology, the fraction of those that actually develop life, FL, and the fraction that becomes intelligent, FI. Finally, we hit sociology, the fraction that develops communicative technology, FC, and L, the length of time they actually survive and broadcast. Multiply them all together, and you get N. Moving on to Section 2, a statistical upgrade, going from simple guesses to actual probabilities. So as science progressed over the last 50 years, researchers realized that plugging static, sheer numbers into this formula just wasn't going to cut it. I mean, when you're guessing numbers for things we don't fully understand yet, like the origin of life, one pessimist's guess and one optimist's guess can literally skew the results from 0 to a billion. The equation absolutely had to evolve. Enter scientist Claudio Maccone's statistical Drake equation. Instead of plugging in rigid guesses, like, say, exactly 350 billion stars, Maccone proposed using probability distributions. By applying the central limit theorem from statistics, we can replace those simple static guesses with a mean value plus or minus a standard deviation. This means the output N isn't just a single number anymore. It becomes a much more realistic range of probabilities, known as a log normal distribution, complete with error bars. Now, what's genuinely awesome about this statistical approach is that it unlocks something called the data enrichment principle. Because it relies on statistical sums, we aren't limited to Drake's original 7 factors anymore. We can continuously add an infinite number of new variables as our scientific knowledge deepens. For example, back in 1961, we didn't know asteroid impacts wiped out the dinosaurs. Now we do. So we can just add a factor for planetary extinction events without breaking the math. As Maccone perfectly put it, this transforms the equation from a simple formula into an evolving Encyclopedia Galactica. All right, Section 3, flaws and new formulations. Let's rethink some of these variables. So, while the statistical upgrade definitely helps the math, some modern critics argue that the original 1961 variables themselves are fundamentally flawed and really need a rethink. Take researcher John Gertz, for example. He suggests abandoning those old metrics entirely. He points out that starting the equation with the rate of new star formation is kind of useless because star formation peaked 10 billion years ago, and we really only care about current stars. He suggests replacing several of the biology and communication factors with a brand new variable, FD. This focuses purely on the fraction of alien technology we can actually detect from Earth, regardless of where or how it originated. And honestly, this makes a lot of sense when you look at how the whole search is shifting. Gertz points out that artificial intelligence, self-replicating probes, or massive world ships could easily outlive their biological creators and spread exponentially across the galaxy. The technology we detect might not even be attached to a living biosphere anymore. Meanwhile, astrobiologist Sara Seager has proposed the Seager equation, which actually pivots away from radio signals entirely. Instead, her formula focuses on sniffing out atmospheric biosignatures, like weird, unnatural gases, on exoplanets using our next-generation telescopes. Which brings us to Section 4, the distance to ET. Just how far away are they? Okay, assuming they are out there and we finally have the right equations dialed in, the next logical question is, how far away is the closest alien civilization? Well, this table brilliantly illustrates the distance law, which assumes a uniform distribution of civilizations across the Milky Way. If n is just 1, meaning, we're the only ones, the math puts that single civilization almost 29,000 light years away, right around the center of our galaxy. If n is 1,000, they're nearly 3,000 light years away. But, and here's the crazy part, if n is 1,000,000, our galactic neighbors are sitting a mere 288 light years away. That is right in our cosmic backyard, well within the range of our current radio telescopes. Finally, Section 5, organizing our ignorance. Let's look at the legacy of the equation. Let's bring it all together and see what this historic equation actually leaves us with today, over 60 years after Frank Drake scribbled it down ahead of that meeting. Frank Drake himself famously reduced his own formula down to his vanity license plate, N equals L. Basically, because the vast number of stars is roughly canceled out by the incredibly small fractions of life and intelligence emerging, the number of alien civilizations ultimately depends almost entirely on L, their longevity. How long does a technological society actually survive before it destroys itself or gets wiped out by some cosmic event? The truth is, we still can't definitively solve it. But as SETI pioneer Jill Tarter so beautifully notes, it provides the perfect scaffolding to organize our scientific ignorance. It forces us to ask the right questions. It directs our telescopes. And it breaks an otherwise impossible cosmic mystery down into chewable scientific bites. As we wrap up this explainer, I want you to consider this final takeaway. The Drake equation isn't just about finding aliens. By searching for L, by looking for how long other civilizations can survive their own advanced technologies without self-destructing, we are ultimately looking for the blueprint to our own survival. So, will we be just a fleeting radio blip in the cosmos? Or will we last long enough to join the galactic conversation? Keep looking up.